Hello, students. We are here to discuss this 7th extra practice worksheet. This involves hypothesis testing, which was our focus in Module 7. Well, with number 1, because as the directions say, I need to set up the hypotheses, I need to carry out the tests, and then clearly state the conclusions. I'll work number 1 on my iPad, but we will be running the tests in R. Okay, so we need to start with the Golub data. Let me run this part in R. The Golub data is in this library MOLT test. And then, as usual, we create this variable gol.fac. We have these two types of leukemia patients, the ALL and AML. Well, we are told we want the H4/J gene. It's in row 2972, and APS, prostate-specific antigen, in row 2989. It's not a bad idea just to make sure that these are the right rows. And in fact, here I call this golub.gnames with row 2972 and 2989. You can see these are the correct rows for these genes. Then I can create a variable for each gene. Gene.h4j comes from the 2972 row, and gene.aps comes from the 2989. Okay, well, now we are ready to get started with 1A. This claim is about a mean. It says the mean H4J gene expression value in the ALL group is greater than -0.9. Well, we need a null hypothesis. We need an alternative hypothesis. Maybe I will just call this mu, although there's really a special mu here. It's the mu of this particular gene expression in the ALL group, but it would be that this mean gene expression is -0.9, and the alternative, this is one-sided. So that would say that mu is greater than -0.9. So we want to use a one-sided t-test. Let's do this in R. What I have specified here in this line is that I'm using the ALL patients, and then I have specified my alternative is greater, one-sided t-test. My p-value is right here, so let's write this. We get p is 0.01601. Now, let's say we're using alpha equals 0.05. Well, this p-value is smaller than that, and so we reject H0, and our conclusion is the mean expression of the H4-J gene in the ALL patients, well, it appears to be bigger than -0.9. One B. Well, you notice once again we have a mean in our claim, but this time we're comparing two different groups, ALL and AML. And, well, in the Golub data, there is a different number in ALL as compared to AML, and so we need to use a Welsh two-sample t-test. But first, let's set up our null hypothesis, our alternative hypothesis. So the null, here I'll use a little subscript, is that the mean of the ALL for this specific gene would be equal to the mean from the AML for this specific gene. The alternative, this will be two-sided, is, well, I can copy and paste, is that the means are not the same. Okay, and as I mentioned, let's do a Welsh two-sample t-test. It is also two-sided. I have used here in R, where I am measuring this gene.h4j using the factor GOL.FAC. We discussed this in our lecture video. Here we go. This p-value is 0.1444. Ooh, well, once again, say we use alpha is 0.05, that's a fairly large p-value, bigger than alpha, and so we fail to reject the null. We cannot conclude the mean expression in the AML group differs from the ALL group. Mean expressions in AML and ALL patients are different. One C. Here we're back to just the ALL leukemia patients. Mean expression value for the H4J gene is lower than the mean expression for the APS prostate-specific antigen. Well, once again, it's about mean expression. So we can think about what is our null, what is our alternative. The null hypothesis, maybe I will use subscripts here. The mean H4J will be equal to the mean of the APS. Here we are just looking at the ALL group. But then this will be one-sided. The alternative is that we have a less than. Okay, we have two options here. One option would be to do a paired two-sample t-test. Let's write this. So one option, and they're really equivalent, would be a paired two-sample t-test, one-sided, of course. But the other option would be to do a one-sample t-test on the difference. In fact, these are equivalent. So maybe let me just mention, I'll do this in orange. In option, I'll label these, say 1 and 2. In option 2, really our null hypothesis is that the difference is 0. And our alternative hypothesis would be, let's see, if we take H4J minus APS, that the difference is less than 0. Now, let us go to R. So here is where I did option 2. So this is a one-sample t-test where I took H4J minus HPS with the alternative less than. And you can see our p-value. We can write it down. The p-value is 0.03886. Well, what about, oh, sorry about that. What about if we did option 1, where I ran a paired two-sample t-test? So what I have done here is entered paired equals true. Now, you notice we get the exact same p-value. In fact, it's the exact same test. This is something we discussed in our lecture video. So I will just leave my p-value as is. Okay, now with alpha equals 0.05, you notice my p-value is less than this, so we reject H0. Our conclusion is that the mean expression of the H4J gene in the ALL group is less than the mean expression of the APS, prostate-specific antigen. All right, letter D. Here is where things change slightly. You notice now this P sub low is a proportion. So no longer are we doing hypothesis tests about population means. We will have a hypothesis test about a proportion here. So P low is the proportion of patients for whom the H4J gene expression is lower than the APS prostate-specific antigen expression. We claim, so here's the claim, P low in the ALL group is greater than 0.5. We need a null hypothesis. We need an alternative hypothesis. The null hypothesis would be that P sub low equals 0.5. And then the alternative hypothesis is P sub low is greater than 0.5. We can use a one-sided exact binomial test. Let us conduct this test in R. Here is the count. I'm calling this count.less. It's just the count of the number of patients in the ALL group for which this gene, H4-J, has lower expression value than this gene. Then, well, we can see how many this is if we're interested. 17. Okay, great. Then our N in the binomial test is just the number of ALL patients. This is 27 if we remember how the Golub data is. In fact, we could ask, what is N? We should have 27. Okay, great. Then we conduct the binomial test. We use P equals 0.5. That came from the null hypothesis, and the alternative greater than 0.5. Okay, here's our p-value. Let's write it down. Our p-value, P equals 0.1239. Well, if you use, say, alpha is 0.5, 0.05, P is bigger than alpha, and so we fail to reject H0. What that says is we cannot conclude that the majority, that would be more than a half, the majority of ALL patients have a lower H4-J gene expression. Well, there's a second part. It says, does this test conclusion agree with the conclusion in part C? You might think that something is wrong because here we fail to reject. We cannot conclude that the majority of the ALL patients have lower H4-J gene expression value compared to the APS prostate-specific antigen. Whereas in C, we conclude the mean expression of this gene is less than the mean expression of the APS prostate-specific antigen. But our conclusion here does not contradict letter C. The conclusion does not contradict C. The reason it does not contradict letter C, well, for example, the average expression can be lower if a few patients have very low expression values, and yet it could be the case that the majority do not have lower expression values. All right, letter E. Once again, this is a proportion claim. P sub H4J is the proportion of patients for whom H4J gene expression values is greater than minus 0.6. And then the claim is that this proportion in the ALL group is less than a half. All right, well, we have a null hypothesis, we have an alternative hypothesis. The null hypothesis is that this proportion, P sub H4J equals 0.5. And then the alternative hypothesis, let's read it, less than. So I change the equals to a less than. This will be a one-sided exact binomial test here. Variable count.ALL, this is the number of ALL patients for whom the gene expression H4J value is greater than minus 0.6. Then, well, we're ready to conduct our binomial test here. In fact, the N was the same N as letter D. Very nice. Well, the p-value here is 0.1239. So with this alpha significance level, this p-value is too big, and so we fail to reject H0. Here we cannot conclude that this P sub H4J in the ALL patients is less than a half. Now, I believe I can make this slightly smaller and fit F on the same page. 1F. This is our last one in question 1. Once again, it is about a proportion, but we are comparing the proportion of ALL patients whose expression of the H4J gene is greater than minus 0.6 to the proportion in the AML patients whose expression of the H4J gene is greater than minus 0.6. So we are comparing two proportions. That was a lot to say. Okay, well, we have a null and we have an alternative. Here, I'm going to maybe call this P sub ALL. The null is that P sub ALL is equal to P sub AML, that the two proportions are equal. But then the alternative is that they're not equal. This will be two-sided. Here, we can use a two-sample test for equal proportions. This was this prop test. Okay, let's go to R. We have count.ALL, count.AML. In fact, we already used the count.ALL above. And then we have the two different N's, the number of ALL patients, the number of AML patients. Then we use the prop test. Our p-value is 0.101. Once again, if we use alpha is 0.05, we fail to reject H0. And so we cannot conclude that these proportions are different. Okay, that was a lot of hypothesis testing all in one question. I think for questions 2 and 3, we will shift entirely to R. Number 2 and 3, we don't have to set up a null hypothesis and an alternative hypothesis. We also don't have to make a conclusion based on a p-value. So these will go a little shorter, I believe. Number 2, suppose the probability to reject a biological hypothesis by the results of a certain experiment is 0.05. The experiment is repeated 2,000 times. How many rejections do you expect? Well, just to get started, maybe I will clear my saved variables. Here we just multiply. So we take 2,000 times 0.05, 100. That's how many rejections we expect. Next question, what is the probability of making less than 90 rejections? We're really talking about a binomial random variable here, where the n is 2,000 and the p is 0.05. So we want the probability that this binomial random variable is less than 90. So this is discrete, which means the probability that x is less than 90 is equal to the probability that x is less than or equal to 89. This is what we can use R, so we can run. You see, we want the probability of binomial random variable with size 2,000 and p is 0.05, that it's less than or equal to 89. And here we have our answer, 0.14. Last question, number 3. On the Gallup dataset, do a Welsh two-sample t-test to compare every gene's expression values in the ALL group versus AML group. Use Bonferroni and Benjamini-Hochberg adjustments, both at the 0.05 level. How many genes are differentially expressed according to these two criteria? Wonderful. Well, because I have cleared all my saved objects, let me load back the Gallup data, and then we create this factor. So here is our p-values. We apply to all the rows in the Gallup data this t-test two-sample where we have used this factor. Then we can adjust. So we have these adjusted p-values, and technically, as we discussed, this FDR are really q-values. And then we ask R, how many for the Bonferroni correction are less than 0.05, and how many for this Benjamini-Hochberg or FDR correction are less than 0.05. And here are two numbers. Bonferroni gives us 103, statistically significant, and Benjamini-Hochberg 695, statistically significant. Well, this is the end of our Module 7 extra practice. Thank you so much, students.